let's introduce Jeremy, who's going to be talking to us about SQL. I do love this topic so much. Okay, can I get a hands up? Who says SQL here? Okay, can all the people who say it right put up their hands now? SQL? I'm kidding, I'm teasing. I'm more of an SQL person myself.
Can I say both? SQL, SQL, SQL. SQL is longer.
It is, it just feels better, I don't know. Anyway, so Jeremy here.
Hello, testing.
How you feeling?
It's great, it's a sunny day, let's go.
Excellent. Well, Jeremy here is the head of product at Juxt, who, may I remind you, play a big part in making this event possible. He is big fan of Clojure, came here for the data log, stayed for the parens, and without further ado, I'm just gonna stop hogging the stage. Give it up for Jeremy, everybody.
Thank you.
Awesome. Well, yeah, thanks. Good morning. So this talk really is quite a pivotal shift for me personally. Like over the last 5.5 years, I've been working at Juxt on this database product. And if you told me back then I was going to give a talk at the Clojure conference about SQL, like I wouldn't have thought you'd be mad. Yeah, like what's happened, and I'm going to talk to you about the shift that we've gone through as the team working on XTDB. But really, the thrust of this talk is what can we do with SQL to make it better? And to start with, I think we should look at the elephant in the room. Sorry, not that one, this one, which of course is Postgres. It's the database everyone knows and loves, or at least that's what the internet has me believe. And it's for good reasons, right? Postgres has many things going for it. Namely that it's everywhere, all the clouds. It's one of the lowest cost databases you can pick. If you're an enterprise and you've spent millions on Oracle licenses for decades, Postgres looks like a great option. It's been around for a very long time. The guy that created it is like an absolute legend in the database field, Michael Stonebreaker. It's very extensible. So people really like Postgres, and it's been very interesting for me seeing it emerge as this victor in the open source SQL world. But you've got to ask, is Postgres fit for the future? I think it's debatable whether the actual code base of Postgres will still be here in 50 years in its current form. I think there are things that are likely to change quite substantially, and there are many good reasons for that. The first is that the original code base, or the architecture, was designed around assumptions that were made back in the 1980s about the number of cores machines had, about the latencies between disk access and I/O, and it was really designed with those assumptions in mind. But things, of course, have moved on a lot, and the rate, the pace of change in hardware is only increasing. So as new hardware gets developed, it's becoming less and less likely that Postgres will be able to keep up. And these aren't sort of my own conclusions, really. This is just me learning from people. So I spoke to this guy earlier in the year, Professor Victor Leis, really top database researcher, and I put him on the spot on the podcast. I said, what do you actually think of Postgres, like internally, the engineering inside it? And he came up with this response, which I won't read, but he did say this at the bottom. I don't think that it's really possible to save it, right? Because all the technical decisions that were made in those early eras, all the other assumptions about how the hardware should work, or how the operating system should work, they were all made incrementally, and there's just such a it's a very fixed code base now. So despite all this, it's still succeeding, right? Postgres is still being adopted and rolled out, but it's just not delivering the kind of performance that it potentially could. So given that, you think, well, why is Postgres succeeding? Well, it's basically just the least bad option of the SQL databases, right? It's got a very strong community. The SQL that it delivers is actually fairly good and has a lot of interesting features. They added JSON support in 2016, or just around that time. And yeah, it's just a very mature ecosystem, and people like that. But technically, it leaves you wanting something more. As an engineer who's interested in mechanical sympathy, it's just not hitting all those notes. So then why is it succeeding? And really, I think the answer is because actually SQL's pretty good, right? SQL has been around for 50 years this year. It's not going anywhere. It's got this sort of Lindy effect thing where everyone keeps investing energy and time into it, so it gets bigger and better. But I don't think it's purely a sort of a pessimistic, oh, well, it's it's not COBOL, right? It does actually do something people like. It may not be the best syntax. So really, Postgres, I think, is riding the wave of SQL, and people have tried over the last decade or so to avoid SQL. But if you look at where all the venture capital money or investments are going, the acquisitions, like people just want SQL databases, or the market thinks people want SQL databases. So that's where we're likely to be for the next 5-10 years at least. That doesn't mean nothing else can be considered. I just think that's the majority of things people are going to be talking about. Now, SQL has been evolving a lot over the last 50 years. Of course, there are like in the original SQL paper, there's a query, and you can still run that query today, right? It has this awesome ability to grow and accrete features for better or worse. But we really should ask, especially as Clojurists with like strong opinions about how languages should work and how simple and decomplected they should be. We really want to understand, what are the things that we should prioritize when evolving SQL, right? We shouldn't just keep adding random features. So I think there are 3 things. Like the first is that we want the database to make our software simpler, right? We want to write less application code and use the database as a point of leverage to increase the amount of work we can get done without having to write lots of low-level looping, procedural, imperative kind of code, right? The database should be doing all that high-performance munging of data. We don't want to be doing that, if possible. So that's one goal. And then there's also the sort of the arguments about concurrency and coordination. But maybe even more important than just simplifying code, you actually just want something that's sound and correct. And even Postgres has struggled with this a lot. I actually, researching this, looked at the Jepson 2020 report on Postgres. And Kyle actually managed to find a bug in the serializable snapshot isolation that had been lurking in Postgres for 9 years, right? So this is like a very subtle thing, and it's about race conditions in concurrent updates. And you get these cycles and something breaks. But the point is that doing complex things is really hard, and in a database, you don't want to do more complex things than necessary. And as application developers, we want to be able to just trust the database is sound and correct. And immutability, of course, is a big part of that. But the other point is that the database should really just make data accessible, right? We shouldn't have to keep writing application code in order to access the data, or at least that's what I think as Clojurists we sort of value first-class data. So here is a summary of just a few things that I think we like about SQL. Data outlives application code, and who doesn't like this concept? I know there's like people that are really into type systems. They have this problem with the idea that data can live independently from the code that defines it. But as SQL database users, that's like a given, right? You can build applications many times. You can tear them down, build them up again, and not have to move the database. So the database can stay the same. That's quite a useful thing. It allows us to experiment very quickly in the language space, or the programming language space. We've got the backwards compatibility argument. So SQL is actually very, very good at being backwards compatible. That's why it's such a mess, frankly, right? It's because people have to incrementally change things, and the grammar is so subtle, so complicated, and it was designed with such arbitrary reasons in mind back in the 60s and 70s, assuming that it would be business users like analysts typing this stuff out. And there are obviously still analysts typing out SQL, but it's not the predominant thing. Most people using SQL are developers these days, or at least in a serious way. Everyone else is clicking on dashboards. I think SQL is very driven by pragmatism. So in the world of big SQL systems, Oracle, Microsoft, IBM, these companies just add on features based on what the market's asking them to add. It doesn't have to be perfect. It's not designed necessarily by committee. There are ISO bodies and other committees which decide and design new features to SQL. But ultimately, it's just, people want unstructured data. Great, we'll give them some JSON operators. That's how SQL works. So it's in response to the feedback that we give them as developers. And ultimately, it's all about the relational model. So this is, something that takes a lot of time to appreciate, is the importance of just having sets. I mean, in Clojure, we have first-class sets. We like sets. We like having the ability to do joins, although we don't call them joins necessarily in Clojure. But that's what SQL's about. It doesn't really say, you should model your data this way. People come up with these normal forms and things, but really it's about you can jam your data in any way you want and query it out any way you want without having to devise the algorithm to do that. You know, you declare what you want and it will figure it out. And that's quite a powerful thing. And ultimately why SQL is important is because people don't want to keep writing these low-level algorithms, especially as the statistics of the data change and the statistics change and your algorithms then need to react to the shape of the data, and the database should be clever enough to figure that out. So we're at Clojure conference, so actually I think Clojure isn't so different on many of these points. You know, we like the fact that data outlives the application code. We value extreme compatibility, backwards compatibility. We also have this desire for things to get magically faster over the time. So in the SQL world, this is because of the change in hardware, right? You don't have to rewrite your SQL queries in order to benefit from extra cores on your hardware, or even different architectures, right? Databases get ported between completely different hardware. And in Clojure, of course, we get the JVM, and the JVM just keeps getting better and smarter every year about how the JIT compilation works. So these are fairly common principles. But Rich had something to say about SQL, and so part of the reason for this talk is to really reflect on, let's rewind the clock 12 years and look at what Rich said were the problems with SQL, and see what we can unpick from that. So he gave this talk essentially introducing Datomic around this time, 2012. And he said two aspects that I want to touch on. Very interesting talk, definitely go and watch it. But we should be avoiding place-oriented systems, and we should talk about the database as a value. That's sort of one of the key messages. And I think that's, if there was a tagline for Datomic, it would be that, I think. But the other one is, he wants the sound model for information modeling. And we'll touch on what that is and how. So Rich said, place-oriented programming is bad. He said place-oriented databases are bad. And what he means by that is whenever you change data, you don't want to lose the reference to the previous version in case someone else needs that. We should be thinking in terms of immutable data structures and immutable values, and he extends this to the database, and he introduces this idea of an epochal time model, which we'll touch on. But the idea is essentially the same as it is in Clojure with atoms, where we decouple the readers and the writers with this very explicit synchronization point. And he has this observation that in order to do that really efficiently, you do need to have this very novel and minimal information model, so that as the information accretes, you can keep track of things over time more easily. So this was sort of his first argument in that part of the talk. The second part, well, actually, there's the third part about how Datomic works, but this is the second part, which is really about data log and what he brings to solve the problem of the information model. So Richard spent a bit of time reading about RDF at the time. I think RDF was still, people weren't sure whether it was going to take off or not. I still think it has yet to. Maybe it will. Couldn't rule it out. But he quite liked this idea of triples. So he took that concept and applied it over time. So you have this extra timestamp at the end of the triple information to come up with these datums. And then the idea is you have pattern matching over that, and you have rules, and this is all very declarative. And it's, if you squint, it is basically like SQL. It's more or less first order logic, and it's declarative, right? You don't have to think of the algorithm. Maybe you don't know what the optimizations are, if any, that are going on under the hood, but at least you can be sure that the end result will be the one you wanted. But really bet big on tight integration with Clojure, because Datomic was designed as a system to extend the Clojure semantics to the disk, right? The data models that work in memory should also work on disk, and that goes as far as the persistent data structures, etc. So yeah, Datomic is a really interesting big bet, like very visionary. Like I think you look at what's happened in the SQL world since, people are adding features still. I mean, what we're talking about now is essentially catching up to what Rich was building all that time ago and continues to build. Also shout out to the Nubank people in the room. So the epochal time model looks like this. The idea is that you have a succession of immutable values or states over time, and that readers or observers can observe those values without interfering with the processes or the functions that move the succession of state from one state to the next. And the database in this world is the identity is that box in the middle, right? So we're saying that the database holds many values. Each time you introduce a transaction, you are changing the database from one value to the next. But that doesn't mean you can't access those old values. You can always access the old values. And that's a powerful idea, and I think a lot of us who got excited about Datomic and this way of modeling information saw that that was just a good idea, right? So why hasn't SQL added this? Well, we'll come on to that in a bit. But I personally took this very to heart, as did many of the people I work with. And so we've been building XTDB, which is another database written in Clojure. It's open source. We've been working on version 2 for the last like 4 years. It's almost entirely Clojure. There is some Kotlin creeping in. This isn't an internal talk, but maybe we should have a talk about why that is. But it's a big team effort. Lots of people at Juxt have contributed over the years. And really our vision here is, can we take the epochal time model to SQL? So SQL has this standard that basically no one talks about or looks at. It's called SQL 2011. So yeah, it's about 13 years old now. But why hasn't anyone embraced that? You've probably never heard of it before. And the reason is because it's a very incomplete standard in a way. It doesn't really achieve what it's set out to do for good reasons, and database implementers haven't really implemented it, at least not very well. So we've gone to the SQL spec and we've like studied it, and we're trying to figure out, can we reshape that or reimagine that spec in terms of the epochal time model and the things that we want from a database as Clojurists. And in particular with version 2, we want to build a mass market engine. So this means, yeah, SQL is like the language people want to look at. It allows us to go to any person in any company and have a conversation that's meaningfully about their data without first having to teach them about Clojure or about Datomic. So that for us is quite a big change. And ultimately, yeah, we want to teach SQL some Clojure tricks. So what does bitemporal versioning mean? That's the big term, and if you've read anything about XTDB over the years, we've probably used the word bitemporality more than we reasonably should have. It's quite a bamboozling word, but really it's just two concepts. One is you record the time that data entered the system. We call this the system time or transaction time, basically equivalent. And we also record the time when something happened. So this is like an idea of modeled time, or maybe there's been a transaction on a previous system and we want to use that timestamp. But it's essentially up to you how you want to use that second time axis. Here it says when the change occurred in the real world. And crucially, SQL 2011 added these two concepts, and it allowed you to then write update syntax or delete syntax, and it wouldn't remove the previous versions. It would actually maintain the versioning automatically. So this is generally quite useful. And it also added some various syntax to capture the properties that this gives you. So it allows you to filter things. For instance, I can take a regular select star and project out these built-in system columns. So valid from, valid to, these are just timestamp columns. And if I run that, I see a single row, right? There's only one thing in my table. If I had 10 things, I'd see 10 rows. But where ID 1 is, I only see one, and that's because by default we filter as of now. And actually this is the inverse to what the SQL 2011 standard says. Actually they say when you do select star on a temporal table, you should see everything, and that would make developing an application quite challenging, or it would continually get in your way. So we flipped the default there. But you do have this ability to override that default. So you can say select for all the versions, and now you can see that all the timestamp information we're having to work out and figure out in XTDB to keep track of when things are valid from and valid to. And as you change data, you need to close the previous intervals. So this is what SQL 2011 is really about. And what does this mean for like application developers who are like trying to solve problems? Well, I think the main one is reporting. If you ever have any reporting requirements, you've probably reached for things like ETLs, out to data warehouses, or read replicas, or audit tables, soft deletes, all these kinds of things, because essentially you struggle with the assumptions that SQL itself was built in 50 years ago about, well, disks are finite, and you need to conserve the amount of disk space you're using, right? So when you update or delete, it deletes the data, like actually deletes it, which is a bit mad for a business user who just wants to know about last month's like sales reports. So SQL 2011 is really intended for solving reporting pains and doing fancy stuff like I want to run last week's report using yesterday's data, right? We've got some new sales figures from some system that's only just come in. So that's the kind of thing it solves. And what we're really, or what I'm wondering is, can I say confidently on stage that actually this model of bitemporality is about taking the epochal time model to the business. It's giving a first-class way of interacting with information that's like we feel when we use atoms, like when we use the Datomic model as Clojure developers, and give that to SQL developers, or like SQL end users, right? People that just are trying to keep track of information. They themselves want to be able to scrub through time and debug their systems. And in some domains, it's actually really important for the decision makers to actually be held to account, and for you to be able to prove what they knew at the point they made a decision, right? I mean, we work a lot in sort of investment banking technology. It's very important to be able to know when someone makes a trade, for instance, that they didn't have access to information they shouldn't have at that time. But in other industries as well, in like healthcare or insurance, there's a lot of red tape and obligations to develop like very specific auditing requirements that say, you know, what was the medical status of the patient when you prescribed the medicine, that sort of thing. So this is a strange way of thinking about databases in a way, like it takes a while to really soak in, but people have been thinking about this for a very long time. Ever since SQL was first created, people have been talking about how to add time into the model. And it really has taken a very long time. And the fact SQL 2011 was 13 years ago and Postgres still doesn't have it sort of indicates just how long this sort of way of thinking has taken to come to maturity. So what we've done in XTDB is to take the epochal time model and to reimagine it in terms of SQL. And maybe the biggest one is people are very used to in SQL databases having interactive transactions. This means that you can take a query, and then you can make an update to a table, then you can do another query, then you can do another update to the table, and then at the end you can commit. And basically that is interactive. And for all kinds of reasons, that's probably a bad idea, right? Because it breaks various assumptions about how like the laws of physics work, and if you build your entire application around interactive transactions, you're basically going to turn the database into this like mess of locks and bottlenecks, because you're trying to make promises that are really hard to keep. It doesn't really respect the natural flow of immutable data. So we ban interactive transactions. We have a single timeline, so we actually write things into Kafka that acts as our timeline of data. But it also provides the isolation and the consistency, not just the durability and the atomicity. And this crucially gives us the ability to do read scaling. So where you would normally take a read replica of a database and not be quite sure how far behind it is from the head of the log, in this, everything's a read replica, right? It's the same semantics as Datomic. So let's have a look at what this looks like. So we've got some SQL queries here. You can see my recent transactions. You can see up on the top left, we've got the first insert I do. So by default, the database is empty, of course. That's V1. Then we insert Fred, and we update Fred, and then we insert a completely new version of Fred using this record syntax, which is essentially like a document API. And then on the bottom right there, you can see we're setting the default system time to version 3 there, basically, and we see a different version count to at the bottom where we're doing it on version 2. So we've added SQL syntax, we've adjusted the SQL 2011 spec to enable you to use the epochal time model, and we think that's certainly very valuable for developers who want to do that debugging and all the good stuff that the system time gives you. So then what about valid time? Well, it gives you this ability to look at facts over time. So whenever you have any requirement that like as an end user of the system, I want to, what did this screen look like last week? If you try and use system time for that capability, you're going to run into all these problems about trying to insert data that's out of order or making any adjustments. It gets very hard when a timeline is immutable to change it, of course. So valid time is this mutable time dimension. It has some nice properties. We actually have this expression timeline as a value. I don't think it's going to catch on, but that's kind of what the vibe is. And you can see in this example where the first state of the database is that Bob likes green, and then the second state of the database is that Carol likes blue, Bob likes green, then Carol likes purple. And so what we're actually saying is that we're like accreting like these transactional layers. It's like a sedimentary rock, and each layer that gets added on top is like the entire timeline of the database. And that's the way to think about, or a way to think about bitemporality. And many people need this. It's not just some obscure thing in finance. Actually, anyone doing anything with like machine learning is definitely struggling with the accuracy problem. They're needing to do back testing of algorithms or models against historical data. That requires making sure you load it in the correct order. So this hops work paper, they build this thing called a feature store, which is for machine learning, and they essentially talk about the comparison with SQL 2011 because it needs the time travel in order to work. We spoke to Kent Beck last year about his views on bitemporality, and he thinks it's really important when building these data systems that you can make the system as correct as possible with what the real world says. So there's lots of people that have like thought this is a good idea, but we haven't really had the tools until now to make it easy, and that's the key difference, right? We take these ideas and make them easy, and then people will actually use them, unlike the spec, which is very complicated. The spec does add this idea of Allen intervals. It simplifies them a little bit because instead of having to do this very complex Allen interval thing, we just have like an overlaps predicate. And I've tried to map it on here. I won't go into the details, but essentially you can say X overlaps Y, and it's like an OR of all of those 8 conditions in the middle, 9 conditions. And we have other predicates as well. But anyway, the point is SQL is growing a little bit. And maybe that's a problem, right? So SQL is a bit big already. And it's not really the compiler target we all want. And this is one of the things that Rich was upset about, I think, with SQL, is that it's not data. But maybe it is. Like, there's a grammar, you can parse it, people do it. And all of these libraries essentially are workarounds for treating SQL like data, and people actually quite enjoy using them. I spoke to the developer of Duke earlier this year, Lucas Eder. He's been building Duke for like 15 years. And I was like researching before the podcast to try and find something that someone said that was bad about Duke. I just couldn't. Everyone just seems to like it. It's a weird way of thinking about SQL, though, because it's like, you are just sort of not trying to write the SQL by hand, but clearly people enjoy it. People have even built data log compilers into SQL. So yeah, SQL, whilst it's very complicated and it's not as simple as we'd like, is maybe good enough. That said, we have been working on a secret language called XTQL. It looks more like this. It compiles to the same relational algebra as the SQL does anyway, so it's essentially just a syntactic sugar for SQL. But it's simpler, right? It's a much easier compiler for us to write. Maybe it's faster. And actually on the right here, James Henderson, the head of engineering, yesterday sent me the screenshot where he's taken Metabase, and I'll explain how that works in a minute, but and essentially injected XTQL into a SQL expression. So that's actually a SQL pane on the right, but he's firing an XTQL query at it. So yeah, we're not going to commit to saying everyone should definitely think this is the greatest thing ever, but we're playing with this idea of like, maybe there's a nicer API surface area. In the meantime, though, SQL's here to stay. There are some questions, though. Rich, talked about this triple model. 6 normal form is essentially what triples are. Do we need to make extra additions to our SQL syntax? Does SQL need to make extra additions to its syntax, like in more general terms, in order to account for these like very small increases in novelty? Or actually, is it kind of okay, especially if you're using it as a compilation target? There's also open questions about, we can't call Clojure core in XTDB version 2. I think there are good reasons for that, but maybe it's good to have some WASM in there, something like that. We need to figure out these questions. But ultimately, I think we all need to ask ourselves, like, what sort of world do we want to live in? Do we want to live in a world where we're all writing more and more Clojure indefinitely, as great as it is? Or do we want to embrace the kind of changes in hardware that are coming and the new algorithms, new intelligence that's emerging, which is able to take something that's really small, really declarative, and just figure it out? Like, it's a very pragmatic stance until you actually have a problem that really has tremendous scale and value. Most of the time, a query optimizer can actually do magic. No, we're still working on ours, of course, but I think over the coming years, as hardware changes, like GPUs become more prominent, query optimizers and the ideas of just pushing more data and compute into the database will only become more prevalent. There's just an open question of, is SQL the way to do it? So we'll find out. So really, SQL is our Trojan horse. It's us taking Clojure into the marketplace. Here's XTDB. Yeah. I spoke to Ray a few weeks ago. He said I should make that an elephant because we've added Postgres wire compatibility, right? So now we actually look like Postgres. And importantly, XTDB makes SQL look and feel like Clojure a little bit. And it has first-class maps and sets. There is a great irony I just want to leave with, which is that actually Postgres had time travel. It already had something basically like the epochal time model, but before it was Postgres SQL. So this was back in 1985 when Michael Stonebreaker wrote this design paper. He said, yeah, we'll just use a timestamp to do an as-of query, and it works. And actually that was in the Postgres code base for like a decade. Then they ripped it out because disk was expensive back then. So nowadays, you can take XTDB, you can take any Postgres-compatible tooling, here's PSQL, point it at XTDB, but it thinks it's Postgres, right? And you can select a version, that works. And I'll just do a real quick demo to show you what that looks like. So I have a code spaces, I have this connection to XTDB here, and I can run through a bunch of stuff. So CodeSpaces is quite nice. We use a Node.js extension called SQL Tools. I can just run some queries. I can see there's nothing in my database. I can see there's nothing in my products table. There is no products table. I don't have to create a table. I can insert straight into the products table with a new record for the first time. Assume that's worked, and then I can run select star on the products. Actually, I've got a bicycle. I've inserted the data. I can do an update. That worked. I can change the price in the update a couple of times. I can select star on the products table again. I see, oh, only the latest price. Okay, of course, because it's as of now. I can access the nested data in the supplier info map, and I can see all the versions, before and after the supplier map. Sorry, I haven't got a mouse. And I can do things like nest many, right? Pull was an important part of the Datalog API. We've added this idea of a nest many thing, so you can just pull in price history, for instance, here. So we've got like an array. So arrays and maps are first class. I can also nest one and just add in some random stuff, right? Where before you had to use like JSON ag and have like data types compressed into JSON. Now it's just all first class literals. So it's very ergonomic, it's very dynamic. And we have our transactions table, of course, which shows the transaction we've just been running. I can run a query as of a timestamp. Of course, that timestamp's no good because that's one I prepared earlier, but I can just take like this one. Well, actually, we'll skip it. Anyway, you can do as of queries. We can see the schema here. We actually represent this as Eden currently, but you can see as we add information to the database, we're just evolving it, right? We're never having to change the schema or alter table or create the table even. So that's quite powerful. We can insert another record. So we'll insert a chair this time. I'm just going to close this. See the second thing we've just added. So there's the chair. There's no supplier info. We can now delete the chair and see it's gone. But we all know it's still there because it's the time travel database. So now we can see that if we select for all valid time, we can see the two periods where it was valid previously. And we can, cardinality violation. Okay, I'll skip that one. And we'll select star just to show that, yeah, we've got the ability to, at any point, see all of the data. So XTDB under the hood is maintaining all this bitemporal information, but as a regular user, you don't have to think about this. There's one that didn't work. It was just an overlaps query, basically. So it said, for a product that's just been deleted, show me all the other products that were on sale, because someone might have bought them at the same time or something. You want to find out the correlations. Anyway, that's the kind of thing XTDB is good for. I'll just leave with one more thing, which is, no, not that one. This one, that's the end. You can try it right live in your browser right now. I would love to speak with you if you have any kind of problems that look like this, because obviously that's what we're building it for. Primarily, that's our USP. So please get in touch. Thank you very much, and especially to everyone in the community, everyone that's worked with XTDB version 1. It's been a real pleasure for us to get to this point where we can come up on stage and actually show you the fruits of our labor, and we hope you enjoy using it. Thank you.